I'm Professor Frank Wicks at Union College, teach mechanical engineering. I'm going to present why the ideal fuel burning engine is not the Carnot cycle, which is too often presumed, but the cycle would now present, which is the ideal fuel burning engine cycle, or the Wicks cycle. That's what the Carnot cycle is. It's usually presented as a rectangle on a temperature versus entropy diagram, but more generally we have the efficiency of any cycle is the net work produced over the heat you add. On this diagram, the net work's area 1, or cycle. The heat is A1 plus A2, and since these are all rectangles, we can show that the net efficiencies has T cold over T hot. T hot is 500 degrees absolute for hot and 500 for cold. The net efficiency is 80%. That's the right answer if we had a constant source of high temperature heat. However, all our fuel burning engines, we produce combustion products at a max fluid flame temperature, and they release heat over the entire temperature range from the maximum temperature down to ambient. So I'm going to modify the derivation of the Carnot cycle and present the efficiency of the cycle. I'll tell you the answer in advance. It's going to be 1 minus T cold log of T hot max over T cold, T hot max minus T cold. Putting in our 2,500 and 500 degrees, we find the best efficiency we can get is 59.2%, as opposed to the wrongfully calculated 8% using the Carnot cycle efficiency for a fuel burning engine. Over here we're going to show how this is derived. The efficiency of any engine is work net over Q hot. The heat end either comes out as net work or heat to the cold side. Therefore, the efficiency is 1 minus T cold over Q hot for any engine. But for the fuel burning engine, Q hot's the mass heat times heat capacity of the combustion products times their temperature change from max down to the ambient temperature. For any ideal engine, the second law says delta S total entropy is 0, which is delta S of the hot side, the source of heat, the delta S of the cold reservoir receiving the heat, the delta S of the working fluid, and this part 0 since entropy is a property. So full cycle means the change is 0. So now going back to the hot reservoir, we had to do some calculus. So the change of entropy of the hot side is going to be the increment of heat over the temperature as it cools off, which is the mass heat capacity over temperature, and which integrates into this, or finally is the mass heat capacity times the log of the cold temperature over the hot temperature. Note that's a negative number, so the hot reservoir gives up heat, so therefore it loses entropy. The cold reservoir is the environment receives all the heat at the same temperature, so what it gets is Q cold over T cold, or equation 7. We can get the heat to the cold side is since this is all constants, the temperature of the cold side times that change in entropy, which we have here. Now putting our equation 8 and 4 back into 3, the efficiency of the ideal fuel burning engine is what we presented up here, or 59.2%. You get the source of heat, combustion products that cool from the maximum temperature down to 500 with a certain mass and heat capacity, so assume there's 100 BTUs here. We have an engine cycle in here that may be any ideal, non-ideal, and then the heat's rejected in a nominally constant temperature environment, we'll call it 500. We can put the same information on this diagram with an engine of 0 efficiency or no engine. The heat that comes from the engine, or from the combustion products cooling off, is area 1 plus area 2. What goes to the environment is area 2 plus area 3. So each one is 100 BTU. But we go to the next step, what goes to the environment is the unavailability of 40.8 BTU, which is what we'd lose with the ideal engine according to Wicks. And the irreversibility is what we could have had but didn't get, is the 59.2%. Okay, supposing someone was to build a fuel burning Carnot cycle, which 100 years worth of thermodynamics is wrongfully suggested, what you'd have to do is first figure the best temperature, the high temperature side. You could use 2,500 to get maximum efficiency but no heat into it. You could use 500 degrees for the hot side. You'd get all the heat into it but no efficiency. the best compromise is the geometric mean between the max fuel temperature and cold, which is 1118 in this case. The net efficiency is going to be the 69% of the heat you get into the cycle times the 55% efficiency of a Carnot cycle once you get it in, or 38 BTU. Going further, the total heat to the environment is going to be 62. The unavailability is still the 40.8. The irreversibility is going to be the 21.2 of this area over here, which was your availability minus the work they actually got, which again is a 21.2 BTU. Or the way we might implement it, what we want is a cycle that's a perfect fit for the availability. So we want something that goes from 1 to 2 to 3. The way to implement it would be with a compressor, but it has to be a isothermal compressor, so we simultaneously put the work in and keep it at the ambient temperature, so we go from 1 to 2. Then we add heat to go to the combustion chamber to go from 2 to 3. Then we go through an ideal turbine that gets us to 3 back to 1. And coming out of the turbine here, we're back to ambient, we're back to our starting pressure and temperature, so nothing's left over. So this point 1 is the same as that point 1. This is ideal, but the problem is we find the pressure ratio is defined as P3 over P1 for the ideal gas. It turns out to be 279, so 1 atmosphere going in, we'd have 279 atmosphere required coming out of the compressor, which is non-practical. But we have defined what's ideal. This could also be a bottom cycle on a gas turbine, which would have obviously maybe an acceptable or something coming off a liquid geothermal. But we define the ideal fuel burning engine and show what it looks like. Now we look at our existing cycles. We have our steam Rankine cycle, which we put down here, and we find out that this is the advantage over a novel cycle. We can utilize the low temperature heat for water heating, and we got the boiling and then the superheating. It's good on the low temperature end, but it cannot utilize high temperature. It degrades high temperature down to the boiling temperature steam mostly. Separately, we can have our gas turbine cycle. In a gas turbine, a compressor, we basically, our combustion products are what goes to the turbine. Here's the exhaust from the turbine. We do a good job on the high temperature end. The downside is we reject at a high temperature. So either one of these separately can be 35 or 40% efficient, but a combined cycle, by putting the two together, we do a better job of getting cycles to meet our availability or exergy. Put the gas turbine on top, recover heat into the steam turbine cycle, and you can get from a 50 to 55% overall efficiency, which is called the first law of efficiency, our net work divided by the heat we put in. But the second law of efficiency is how well we did compared to the best we could do. And using these numbers, with the most advanced combined cycle, they claim about 55% overall efficiency. Ideally, we can only get about 59.2%. So you have a second law of efficiency of 93%, which is basically showing you're doing about as well as you possibly can ever do on a fuel burning engine with existing combined cycles. 1991 in an Intersociety Energy Conversion Engineering Conference over in Boston, under the title of the Thermodynamic Theory and Design of an Ideal Fuel Burning Engine. So much of this material was presented then. I've used this and other people use it for a number of second law analysis of engines since then. Here's a newly published Thermodynamics book by Professor Chih Wu of the United States Naval Academy, Thermodynamics and heat-powered cycles. And in here he has examples of the Wicks cycle for the non-flow piston cylinder version and the flow version of the turbine compressor. And I would hope and expect that all viable thermodynamic books in the future, credible thermodynamic future, books on thermal in the future should define the ideal fuel burning engine or the Wicks cycle and give related examples like Professor Wu has done in this book.